Hello! Welcome back to EEforEveryone and part 9.5 of the Plant Light project. You might be wondering how we got here. You know, project limbo between part 9 and 10. If you noticed in the previous parts of this series when we were talking about some of the theory behind this lamp, I kept referencing the future parts of this series by number. Unfortunately, I scheduled way too much content to be jam-packed into part 9. Consider this an early lesson in projects that they are rarely as simple in reality as they are in your mind. We're going to discuss the current regulator that we've been talking about in part 4 of this series. Instead of talking about the theory of operation, we're going to measure the current regulation performance at a few set points as RMS and peak-to-peak values. We will run the lamp at a few different current set points and evaluate how close the current regulation of the LED channel is to what we would expect. In this case, we'll be evaluating the blue LED channel. 100% duty cycle from the microcontroller would result in 333 milliamps of current flowing through the LED channel. 0% would result in 0 milliamps of current. Measuring current is kind of a tricky thing since one needs to break the circuit to properly measure current. That's why I added the 0603 resistor pads across one LED in each loop. Since the voltage dropped across the current shunt in my multimeter will be much less than the forward voltage of the LED, we know that nearly 100% of the current will be flowing through the multimeter. If you don't know that, then you should check out my video that talks about how to control the brightness of an LED. Hopefully that will help to clear things up. When it comes to the time domain and frequency domain measurements that require an oscilloscope, we will measure the voltage across the 0.3 ohm shunt resistor in series with each set of LEDs to measure the current. We can use Ohm's law then, volts equals current times resistance, to translate this voltage and resistance into a current measurement. So I have the workbench set up for us. I've soldered wires to each side of one of those current shunt resistors and to one side of each of the 0603 pads on the bottom of the blue channel. All of the other channels have been disabled, and then these two wires from the bottom come over to the multimeter, which is in current mode. The voltage will be measured by the analog discovery. I've been meaning to spring for a proper oscilloscope for a while, but frankly, I'm shocked at how well this pocket oscilloscope works, and well, I haven't really had an application that needs it yet. When we're measuring this performance, the plant light is modulating each channel from 0 to 100% brightness, which is requesting from 0 to 300 milliamps of current behind the scenes. What's being called 100% brightness is truly 90% of the maximum 333 milliamp output of the LED channel, but we software limited that to 300 milliamps in the actual firmware. So with that in mind, let's gather some data. Step 1 here will be to take our voltage and plug it into the plant light. So far, so good. There we go. We have turned off all the LED channels. Set to milliamps. With the current probe set up, I have the frequency content plotted on the waveforms window, as well as the time domain signal measured across the current shunt. And then here I've got the multimeter measuring RMS current, and this spreadsheet here for saving data. All right. So let's start putting in the current. So we will set the lamp to 5%. Here I'm measuring, got my current probes backward. This around. measure 9.5 milliamps. Okay, let's bump that up to 10%. We are measuring 23 milliamps. We're going to add on some cursors here. So we're going to 20% brightness at 52.5 to 30. $81.9. 40. 111.4. 5. 50%. 141. 60%. 170.6. 70%. 200. 80%. 230. 90% brightness. 260, and finally 100% brightness, which is measuring 290 milliamps. All right, and now we're looking for the peak-to-peak current ripple, which I gotta turn this down. These are getting really bright, or really hot. So turning down the brightness here, because these LEDs are getting quite warm without their heatsink. I noticed that on this waveform here, it's not behaving how I expected. In fact, you'll have to excuse the noise. This isn't a fully differential setup, and I think there's some AC coupling through the power supply onto the DC rail, and this is referencing ground of the computer, and yeah, so there's some noise there. I could try AC coupling. That's all right. I'll leave it. It's fine the way it is. So it looks like what we're seeing here is the way that this IC is controlling the current is by giving it peaks of the maximum 333 milliamp current, and then just pulse width modulating that to achieve our total brightness, which is not what I expected at all. I expected some sort of linear average that would then be used to dynamically change the set point, which that may have been an unreasonable assumption at any rate. So as I go ahead and increase this PWM, we can see that on the frequency domain graph, there is a clear peak at 160 kilohertz, which is undoubtedly the frequency where the switch mode power supply is switching. That's great. And as that is less and less part of the signal, the noise takes over. Looks like the battery just died on the main camera, so looks like you'll be dealing with this view for the rest of it. Sorry about that. So we've got the DC RMS, and we've got the peak-to-peak. So for peak-to-peak ripple current is around 400 milliamps, and the average is around 130. Oh, this is not at 5%. 25%. The ripple current is again 400, and the average is around 140. Moving up to 50%. Its peak to peak is again around 400. And the average current is around 210. 75%. Again around the 400. And we're looking at around 260. Getting up to 100%. Looks like around the 400 again, and then nearly 300. There you go. The important thing to keep in mind with measurements like this is that oscilloscopes are generally less accurate than a multimeter at measuring RMS currents and voltages. It's just a different tool for a different job. But we ran through some measurements here, collected some data. I'll make a couple graphs that try to illustrate the points and just shares what I've seen in this data with you, and I'll turn the main camera back on, and then we'll discuss. All right, talk to you in a minute. So I've made some graphs, as you can see on the screen, and I think that I misspoke before. That 100 or so kilohertz that we were seeing in the FFT, I'm almost 100% sure that that's from the PWM of the microcontroller, because I've already characterized the switch mode power supply itself, and that exhibited a switching frequency of around 750 kilohertz. So just wanted to clear that up. So in these graphs, the one on the bottom left here, it is showing a graphical representation of the measured current plotted against the expected current and the percent difference between what we measured and what was expected. This is a pretty telling metric because the percent difference will show how close we were to our set point. And we can see that at very low percent expected currents, the percent difference is pretty large, actually. Around 40%. We were about 40% off from what we expected to what we got. But as we got closer and closer to 100% of the set point, it was starting to converge where the percent difference was approaching 0%, getting as low as 3% from our set point to what was delivered to the LEDs. So that is the switch mode power supply tolerance, the current shunt tolerance, tolerance on the timing of the PWM out of the microcontroller, that along with the action of the BJTs that are actually disabling the switch mode power supplies. So the stack up of all of the tolerances got to around 3%, where the PWM, I guess, the PWM was no longer, the PWM was still a factor because that was about 90%. So all those tolerances stacked up ended up being around 3% different. And then the graph on the top over here, that's showing the average current and the peak-to-peak ripple current in milliamps. As we were walking through, I noticed since it was PWM controlling the current to the LEDs, that means that the average current was changing because the PWM duty cycle was changing, but the peak-to-peak ripple current didn't change at all since that was just going straight to the maximum. And then that was, of course, with tolerance of the analog discovery factored in, which was not an accurate measurement of the peak current, since we know the peak current is set to 333 milliamps, and the PWM ratio works out correctly with the RMS current the multimeter was measuring. So the peak current measurement was wrong. There's some noise on the signal that we were measuring that's easy to explain if you know how 60 hertz noise can get in a measurement like this, but off the top of my head, I don't think I can explain it well enough to really try here. So I can try to revisit that more, collect my thoughts, and speak to it a little more completely. So as best as I could measure, the peak-to-peak ripple current was around 400 milliamps, and the average current was, of course, coming up to the 300 milliamp set point, which we would get at 100% current setting. So overall, it's not too bad. A 3% difference at high currents, around 6% difference from 50% up, and pretty poor performance at 5 to 20% brightness, but I doubt that someone would really be wanting to use the lamp at that level. That said, now that we've characterized this lamp, we can modify our PWM equation that converts from a current set point to the PWM value to send out to the hardware. And we can take this data and compensate the algorithm it's using so that we will get approximately 0% difference from 0 to 100% of the range using a piecewise or more complicated function. I had a lot of fun measuring the performance of the current regulation circuitry on board this plant light with you, and I enjoyed spending this time at the workbench with you. If you think that current regulation is cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving us a comment down below, letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!